Okay, good afternoon, everybody. Welcome back to day 3. Okay, we got Joseph and Fady and Susan and Surly and Victor and Raj. Okay, and Sierra is here. That's good. Good to see you. Is Raj here? Is Raj?
Yeah.
Okay. Um, and Anthony is here. That's good to know. Anthony laughs at my jokes, so I appreciate him being here. Raj is here. Okay, Gabriella's here. Nice. Okay, cool. Okay. Okay, so Victor says, we said if we don't have a subscription by today, you're going to drop us. But if we have the free trials, that's still okay. Yeah, absolutely. But do not let your free trial expire. Okay. If you let your free trial expire, you're going to run into issues. Does that make sense? Okay, got it. Good. Okay, perfect. Okay. Halal here is
I have a
here.
question about exams.
Yeah, sure. So everybody's freaks out about exams. Okay.
Um,
Yeah.
no, I'm just trying to cover my bases.
Okay.
So I know that we're using the Proctorio software, right?
Yes.
But we also have to scan and upload our exams.
Yes.
So are we doing that with our phone? Like, is that going to be
No.
okay? Okay, so what are we using?
You're using your computer to
Okay.
upload the file. So if you want to send the file, if you want to use your phone and then email it to yourself,
Mm-hmm.
you can do that. I'm not limiting the number of windows that you can have open on your screen.
Oh, okay. So we can use our phone and then just upload it to Canvas.
Yes.
Okay.
Absolutely.
Yeah, I was just not sure how
But it
that's going to
has to be a PDF. It
Yeah.
cannot be a JPEG or an HCIF file or any of that stuff. So if you have a PDF scanner,
Yeah, so if I scanned it and then like
yeah,
messaged it to myself through iMessage, is that okay?
yeah. However
Okay.
you can upload it into Canvas is fine.
Okay,
You know,
cool.
I mean,
Thank
if
you.
you want to use an iPad or if your phone or you know, um, whatever, however you want to do it, it's fine. Okay. The thing though is that wherever well, I don't know if you're going to be able to upload it through your phone. That's the problem. Yeah, I think you're going to need to get it on your computer somehow and then upload it into Proctorio through your computer. Does that make sense? You're not going to be able to upload it through the app, through the Canvas app.
Yeah, so I would just have to download it onto my computer and then
Yes,
upload
and then
Canvas. Okay.
upload it into Canvas from your computer.
Okay, sounds good. Thank
Okay. Okay. Any other questions? Would you be able to go over homework problem 6.3, number 11? Sure, absolutely. Victor asks. Okay, so
Same question.
yeah. Oh, same question. Okay, 6.3, number 11. Okay. Um, and then Jamson, is that how you say it? Jameson?
Oh yeah, you got it the first time, Jamson.
Jamson. Okay, Jamson. You saw that I updated your grade. You
Oh,
see
cool.
that?
Yeah, sounds good. Thank you.
Okay, sounds good. Okay. Yeah, 6.3, number 11. Let's do 6.3, number 11. Can you share your screen, Victor, and show me 6.3, number 11, or do I need to get that out at this point? I mean, I would prefer you do the work instead of me since it's your question. 1 second. Absolutely. You got it. Okay. 1, 2. Oh, were you literal? You weren't literal. Okay, sorry. Okay, so. Oh, there you go. That was good. Okay. Find the equation of the tangent line. Okay, to the curve of the following. Okay, so did you do implicit differentiation here? Okay, so I think I sent somebody an email back saying, look, you had to write it as an equation. Okay, after you do implicit differentiation, you have to write it as an equation. Okay, so you find the derivative, which is your slope, and then you have to write this thing as an equation, y equals. But if you still have an issue about this one, that's fine. Let me write it down. So x e to the y plus y e to the x is equal to 5, right? Okay. So you can go ahead and stop sharing your screen at this time. Okay, thanks. So let me go and I'll share my screen. Okay. And let's pull up my stuff here. Okay, and let's see what we got going on here. Okay, so x e to the y plus y e to the x is equal to 5, right? Is equal to 5. And what was the point? The point was 0, 5, was that right? Yeah, okay, 0, 5. Okay, perfect. Okay, so at the point 0, 5, right? Okay, so yeah. So let's do implicit differentiation here. So we're going to get derivative of the first is 1 times e to the y, okay, which is the second, plus derivative of the second, which is going to be e to the y prime times the first, right? Plus, let's do the next, derivative of the first times the second, plus derivative of the second times the first, which is y, is equal to 0, right? Okay, so I've got, these are x's. Okay, so I've got my e to the y's, I got my e to the x's here. Okay, so, and I got a y prime, so I got my y prime. So what I'm going to do here is I'm going to, I'm going to collect my terms for y prime. Okay, and I'm going to factor out my y prime. Okay, so y prime e to the y x plus e to the, right, e to the y prime, okay, plus e to the x, that's it. Okay, and then I'm going to toss everything else to the other side. This is going to be negative e to the y, right, negative e to the y, and then it's going to be negative e to the x. Gosh, my handwriting is so bad today. What is wrong with me? E to the y, and then minus e to the x, y, right? So far, so good. And then we're going to divide. Okay, and this is e to the y x plus e to the x, right? Okay. And so we want this to be 0, 5. So x is 0. So x is 0 when y is 5, right? So we want to kind of figure out, well, what's y prime going to be, right? What's y prime going to be? Okay, so this is negative e, right? Negative e to the 5th power, negative e to the 5th power. This is going to be negative e to the 0 power, okay, but then that's minus 5, so that's just minus 5, all over e to the 5th times 0, well, that just goes away, and then e to the 0, which is 1, so that goes away too. So y prime is negative e to the 5th minus 5, right? So that's my slope. That's m. So now we're just going to use the fact that the y-intercept here is 5, and we're just going to use slope-intercept form. Y equals negative e to the 5 minus 5 times x plus 5. Okay? So make sure that you write it as an equation. Okay, so does that help? Does that help answer your question?
I guess, Professor, I did the same thing and it said wrong.
Yeah, you did because you didn't write it as an equation. You only wrote it as an expression. It says write an equation. It didn't say write an expression. Does that make sense?
Yeah, I understand.
Okay, good. Okay, there's a big difference between an expression and an equation. One has an equal sign and one does not. Okay, other questions? Okay, any other issues before we start today's material? Okay, with that said, we'll move into today's material, 6.5. Okay, Sierra asked for application yesterday, and so I've geared my lecture today toward application toward economics, which I believe, Sierra, that is your major, right? So I went through and we're going to do a lot of economic stuff. We're going to do a little bit of biology. You engineering majors, you can hold on. We will get engineering and computer science applications in there as well. Okay. I can't do you know, I gotta spread out the applications and love to everybody, but it is what it is. So again, the highest number of majors in this class right now is engineering, so which makes sense. Not a whole lot of engineering application in this class. That's the next one. That's Calc 3. Calc 3 is basically all engineering application. So, but you got to learn to walk before you can run, right? Does that make sense? So engineers, Calc 3. There's your applications. Okay, and your computer scientists who want to do mathematical interfaces. Okay, but for the rest of you lay people, the applications will be more geared toward business and biology in this class. Okay. Okay. Well, with that said, let's get to it. Okay. Question? No. Okay. Make sure you're muted. Okay. Especially if you have rambunctious family members in the room with you. Okay. I kick my kids out. Be gone with you and your bad self. Okay. So, not allowed in here with me. It's my domain. Get out of my room. Okay. Anyway, I digress. Okay, 6.5 is on exponential growth and decay. Let me mute whoever's not muted right now, because that's going to be a tad annoying. I'm going to go to the mute all, and I'm going to mute everybody. Here we go. Mute all for you people. That was not the right. That was not the right one. It's all good. Okay. Let's go back. Okay, can let me share my screen again. Okay, hopefully everybody can see my screen now. Okay, 6.5. Okay, thank you, Sarah. Okay, 6.5 is on exponential growth and decay. Okay. Growth and decay models. Okay, exponential growth and decay. Let's talk about exponential growth first. Exponential growth looks like this. It grows exponentially. Boom. Nice. Okay, it grows exponentially, just kind of like what COVID is doing right now in California. It's growing exponential growth right now, okay? That's the curve, looks just like that. Okay, so we've got exponential growth. This point here, okay, which is my y-intercept, okay, we're going to call that, what are we going to call that in this one? We're going to call that C. We're going to call that C for a constant. Okay, that's a constant. That's going to be my y-intercept. Let's put that back. Okay, let's put C back here. Okay, C for constant. Okay, that's going to be the constant, or a lot of times that's going to be my starting place. Okay, in my exponential growth, because say that we wanted time, right? T for time, and maybe this is population over time. We can't really go back in time, and so this C would be my initial value. Does that make sense? When time is 0, okay, let me write that better. Try hard. Okay, initial value, okay, is C. So if say that we're in T, okay, that's our initial value. Okay. Given, wow, this is, okay, given, okay, y is equal to C e to the kt. Okay, where this is exponential growth model, exponential growth. Okay, if we take the derivative of this, y prime, okay, C is a constant and K is a constant. Okay, C is a constant and K is a constant, so C just stays out in front. Okay, I'm going to drop the K down, and then I'm going to get e to the kt. Now, why is that? Well, what's the derivative of e to the kt, this thing here? Well, it's itself times the derivative of kt, k times t. Well, what's the derivative of k times t? Well, derivative of k times t is k. Does that make sense? Maybe I'll write it like this. Okay, e to the kt times k by the chain rule. Okay, so that's e to the kt times k by the chain rule. Now, what I'm going to do is I'm going to rewrite this guy, y prime is equal to, okay, k times c e to the kt. And that's kind of interesting. Okay. It's basically, what we just started with was c e to the kt, right? C e to the kt, that's what we started with. And what we ended up with the derivative is y prime equals k, which is a constant. Okay, that's going to be the exponential growth rate. Okay, this is the rate of growth. Okay, times my original function. So we could basically write this, okay, and say that this is dy dt is equal to k times y. That is how we can express this. The derivative of the function is just the constant, the growth rate times the original function. Okay, that's a really nice property of exponential growth. Okay, with the natural exponent here. Okay. This guy, by the way, is called a differential equation. Differential equation. And it's just an equation that has a derivative in it. That's why it's called a differential equation. It's just an equation that has a derivative in it. Okay, if you ever have a equation that has a derivative, it's called a differential equation. Okay, so if f of x is equal to c e to the kx, okay, we're not using t, we're just switching variables to x. We're going to generalize this for all functions, not just ones involving t or time. Okay, then f prime of x is equal to k times f of x. Okay, that's basically what this is saying. These two things are the same thing. Okay. Basically, all three of these things are the same thing. They're all the same. Okay, equals, equals. Okay. Okay. Okay, number 1. Okay, find the general form find the general form of the function whose derivative is given. Okay, whose derivative is given. Okay, so A, we're going to do dA dt is equal to 5a. Okay, dA dt is equal to 5a. So what did we have before? We had dy dt was equal to ky, right? And what was the answer to this differential equation? Well, that was our ce to the kt, right? Wasn't that y equals c e to the kt? Right? Wasn't the function whose derivative was this thing, the original function was my exponential growth model. So what do you think the function here is going to be? Any ideas? Well, what's the variable? The variable is a, right? And then times a constant. A equals c, right? C, which is a constant. E, what's k in this case?
5.
5, very good, thank you. Okay, thank you, Sierra. Thank you, Joyce. Okay, awesome. 5, so this is c e to the 5t. Okay, and so that's my, now that looks really similar to something that we covered yesterday, right? So we'll get to that in a minute. But that looks really similar to that PERT account, right? That continually compounded interest that we talked about yesterday. Okay. What about B? Okay, B is dp dt is equal to kp. Okay, well, what's this going to be? dp dt equals kp. Well, again, it's just a change of variable, right? So then this is going to be p is equal to c e to the kt, right? Boom. Okay. Okay. So let's think about this a little bit. If f prime of x is equal to kf of x, okay, when f of x is equal to c e to the kx, okay, then k is equal to f prime of x all over f of x. That means that the ratio from the derivative to the original function is always the same value. It's a constant. The ratio of the derivative to the function is always the same value. It's kind of interesting. Okay, so this implies that the ratio, okay, the ratio of the derivative of the function to itself of the, this is why we have erasers. Okay, the ratio of the function's derivative to itself is always constant. Constant. Okay, it's always constant. Okay. Okay, always the same value. Okay, this function, which function? F of x equals c e to the kx, okay, is called the exponential growth model. Okay, exponential growth model. Okay, so f of x, okay, is equal to c e to the kx, where c is a constant, or what we will call okay, or initial value. We're going to start calling this thing an initial value. Because what happens when x is 0? What is y? What happens if I plug a 0 in here for x? What happens to the function? What is it equal to? Put it in the chat box. Exactly, it's c, right? It's c. So when we plug in 0, the at time 0, wouldn't the initial value be c? Yeah. Okay, or initial value where c is a constant. Thank you for all you that participated. Okay, where c is a constant or an initial value. Okay. Okay, and k is called the exponential growth rate. This is the exponential exponential growth rate. Okay. Okay. So good stuff. Okay, a couple of things. Okay, so this is for my biology majors. Biology. Okay. So my biology majors, this is for you guys. For population growth, okay, for population growth, the function is P, whoa, I don't know what happened there, is P equals P naught e to the RT, okay? P naught e to the RT, okay? Where P naught is the initial population. Okay, so that's for my biology majors, okay, or chemistry majors, because we could talk about, you know, virology and how you know, a virus or a bacteria grows in a petri dish, okay, based on this stuff too. So I don't know, you can think about chemistry or biology for those applications. Okay, now what about finance? Finance. We're going to talk a lot about personal finance today. Okay, finance. Okay, for finance, okay, or business, okay, or personal finance. In finance, for monetary growth, the function is modeled as what? What do you think that? What do you think in finance it's modeled as? Anyone want to take a guess? It's what I covered the last 20 minutes of class last time. Yeah, exactly. Thank you, Anthony. Okay, it is the PERT account. Okay, A equals P e to the RT. That's that PERT account. Okay, for monetary growth, that's A equals P e to the RT. Okay, where P okay, where P is the principal amount. Okay, that's the principal amount. Okay. Okay, let's do an example here. Number 2. Okay, suppose P dollars, okay, is invested at 7% interest rate, at a 7% interest rate. Good luck getting that anywhere. Okay, interest rate. Okay, some of this stuff is, you know, we kind of massage the problem sometimes to make the math a little more interesting than, you know, what we get in real life. And so there is a cartoon, a Peanuts cartoon, where Lucy in Peanuts, she says, only in a math problem can you buy 1,000 watermelon and nobody asks what the hell is wrong with you. Yeah, so it's a funny cartoon. It's by Charles Schulz. Okay, before he passed away. Okay, but it's very true, right? It's very true. Only in a math problem can you know, say Sally goes to the store and buys 1,000 watermelon. Well, okay, sure, sounds good. Okay, so suppose P dollars is invested at, this should be an at a, oh, I forgot the at a 7% interest rate. Okay, y'all ain't never done that before? Oh, that's cute. Okay, suppose P dollars is invested at a 7% interest rate. Okay. Interest rate at, what else do we want? Such that, okay, such that dAdt, okay, dAdt is equal to 0.07a. Okay, so this is my differential equation. Okay, so we're going to take the differential equation and we're going to translate that into our general equation. Okay, for a, we want to know what's a going to be equal to. Well, a is equal to p e to the rt, right? So that's going to be p e to the 0.07t, right? Okay. Okay. So p e to the rt equals p e to the 0.07t. That's going to be my equation, right? Okay. Okay. So let's look at a here. A is if $100 is invested into the account, okay, is invested in the account for 1 year, okay, time equaling 1, what is the balance? What is the final balance? Okay, so again, this is just plug and play. This is pretty easy. A equals, what's going to go in for P? Well, obviously 100, right? Okay, 100 times e to the 0.07, and then what's our time? What's t in this case? T is going to be 1, right? It's just going to be 1. And so when we put that on our calculator, okay, so, man, the calculator is really slow. Okay, so when we put this on our calculator, we're going to say 100 times e. Okay, I got to go second here to get my e. E, okay, no, I don't want e to the 100. Okay, I want e. Why did it do that? Why did it do that? Oh, maybe I have to do, maybe it's reverse notation. Okay, so let's clear this. Clear all. Okay, let's try it again. Okay, so for this calculator, it's reverse notation. So this is going to be 0.07 and then e. Okay, and then I'm going to multiply that times 100. Okay. Okay, so it's 107.25 or $107.25. That's good to know. $107.25. So I made an extra $7.25 for the year. Okay, by investing my money. Okay, saving it wisely. Okay, let's do a more interesting problem. What's this one here? B. It says, what is the time to double the initial amount? What is the time to double the initial amount? Boom. Okay, basically how long is it going to take for me to double my money? That's what I want to know at 7%. Okay, how long is it going to take for me to double my money? Okay. No, stop. Don't even say that. How could you, Nathalia? Don't. No, okay? The curve is going back up, and I need my toilet paper. Okay, so don't cause another scare. Okay? Just don't do it. Okay? Like, people are all like hoarding when there were like 500 cases in California. And now there's 256,000 cases, and everybody's like, oh, it's all good. Like, it's the end of the world. Before, when there was nothing here, right? And now that there's a pandemic, it's all good. So don't, that's my mathematician. What I did in the very beginning is I mathematically modeled, you know, in my spare time, which has been a lot since I don't have any friends and nobody lets me out of my room. So I have been modeling the whole thing since the very beginning, since they sent me home in March. So I have run my own mathematical model, and maybe I'll publish that someday. Maybe I'll get some rights or something to it. But I have run my own model. So anyway, that's what mathematicians do in their spare time, as fun. That's what we do as fun, as we stay up all night and run virology models. Doesn't that sound fun to you? So anyway, okay, what is the time to double the initial amount? Okay, double the initial amount. Okay, A is equal to PE to the 0.07t, right? That's our equation. Okay, our initial amount was 100, and what do we want to do? We want to get our final amount as 200. So this is e to the 0.07t. I want to solve this for t. I'm going to divide by 100. Okay, so if I want to double any amount, wouldn't I just be, if I wanted to take $1 and double it, wouldn't I just get $2? Right, so it's just a ratio of 1 to 2. So that number here is always going to be 2 if I double. And then it's e to the 0.07t. Okay, and so now what I'm going to do to both sides, what should I do to solve for t here? Any ideas?
Natural log.
Absolutely, thank you, Fady. Natural log, thank you for, wow, that came in fast. You guys are fast. Okay, take ln on both sides, natural log, very good. Victor, Sierra, awesome, you're doing well in my class. Okay, yes, okay. Alyssa, thank you, take natural log. Surly, thank you for that. Is it Eliel? Is that how you say that? Or Eliel?
L-E-L.
L-E-L. L-E-L.
Yeah.
Right? Like lol, but lel.
Exactly.
Exactly. There you go. Okay. See, you make those associations, you're never going to forget things. Okay, that's how our brains work. Our brains work by association. Okay, so LEL, thank you for participating. Okay, that's the class participation. Okay, so it gives good vibes to me when people participate in my class. That's how I know you're alive and you're paying attention. Okay, it's the good vibes. Okay, 2 is equal to, so let's take the natural log of both sides. Natural log of both sides, somebody knows their math, that's good. Okay, that cancels out. We're gonna get the natural log of 2 over 0.07 is equal to t, right? Okay. Okay, and so t, okay, if I plug this into my calculator again, oh, I should just keep this thing out. Okay, it takes forever. to load. Natural log of 2, so I want 2. Again, this is reverse notation. Natural log of 2 is about 0.693, right? 0.693, and then we're going to divide by 0.07. No, I don't want to divide by 7. I want to divide by 0.07. Okay, 0.07. Okay, and I get about 9.9 years. Okay, or roughly 10 years. Okay, about 9.9 years. Okay, or we'll just call it 10 years. I mean, if you have to wait 9.9 years, aren't you willing to wait that extra 0.1 year? I mean, come on. Let's just call it 10 years. Okay, now, this is used in finance a lot. Okay, has anybody ever heard of the rule of 72 in personal finance? The rule of 72? No? Okay, yes? No? Who? I have one person? Yes, okay, Susan says yes. Frederick says yes. Isabel says no. Okay, well, if you're a no, that's okay. That's okay. You just don't. I just want the people who are yeses. Okay, rule of 72. Susan has said, yeah, Susan. I know that you have. Okay, that. Okay, I don't know. It's like the younger generation. They haven't heard this yet for some reason. I just don't get it. Okay, but maybe they just don't have any money. That's the problem. They have no money to invest. Everybody's broke. Okay. Yeah, exactly. We get it. Yes. Okay, so the rule of 72, okay, is that if you take 72 and you divide by your interest rate, okay, that will tell you approximately how long until your money doubles. Okay, now this really should be called this is the rule of 72. Okay, this really should be called the rule of natural log of 2, but that doesn't roll off the tongue as nice. Okay, it really doesn't. Is not fun. Also, the reason that 72 is used is for people who are not mathematically inclined. 72 has a ton of factors. Okay, it is divisible by 2, 3, 4, 6, 8, 9, 12. It's divisible by, you can divide by 10 easy. You can divide by a bunch of stuff really easy here, right? Okay, a ton of factors. Okay, 2, 3, 4, 6, 8, 9, 12, forever, right? Okay, it has a ton of factors. So this is just kind of like, oh, you know, it's right up. So if I said, I want to invest, okay, at 9%, approximately how long is it going to take me? Approximately how long is it going to take me to double my money? Well, what's 72 divided by 9? Anyone can do that? If you can't do that, you're in the wrong class. I'm just letting you know right now. Okay, just
8.
8. Wow. Yes. Somebody's on it today. Okay, so 8 years. You see how easy this is? Okay, let's take a harder one. Let's do 6%. Okay. Now I changed my tone there because now I feel like I'm teaching 4th grade. Okay, 6%. How long would it take to double your money? 12 years.
Oh.
Yeah. It's amazing like that. Okay. Now what you're really doing is you're really taking the natural log of 2 and you're dividing by 0.06. And that'll give you exactly what you want. Okay, but this is your doubling time. So the time that it takes to double is natural log of 2 over r. That's your doubling time. Okay, it's called the rule of 72. Okay, because people don't, in personal finance, don't understand natural logs. Okay, you have to leave that to the economists. Okay, so, right, Sierra? Okay, or the business administration majors. They know how to take their natural logs. Okay, but those people selling life insurance, I don't know if they really know how to take their natural logs. I don't know. I mean, maybe the people that have the Series 7, but not the, I don't know, the Series 6. I don't know, you know, people that are out there doing that stuff. I don't know. It'd be interesting to see if they could do their natural logs or not. But anyway, yeah, exactly, Sierra. You're just like, yep. Okay. So again, you know, people. Okay, I don't know what it is. What the mathematically people just don't like math. They don't. They just don't like it, and I still don't. I don't fully get it, but that was because I really pissed off my math teacher in high school. I 2 times I pissed off my math teacher. Let me tell you how I did that. Okay, there was 2 times. Okay, and he was really cool. I actually ended up going back to, his name was Mr. Mutolo, and I actually went back to him and student taught for him right out of college. So I actually got to student teach my old classroom where I actually took my own math class in, my own Algebra 2 class. I got to teach the same. That's kind of amazing, right? Like, who gets that opportunity? Who gets the opportunity to go back into their own classroom where they learned and then teach? So I was pretty lucky. He was so amazing and generous. But I did piss him off a couple times. So let me tell you how I pissed him off. Can I say that? Can I say pissed off? Is that allowed? I mean, this is all being recorded. I hope I can say that and not get in trouble. But anyway, so yeah, the first time was I went up to him. I think I was a sophomore in high school. I was really stupid as a sophomore in high school. My freshman year, I hated everybody. So they were just all idiots, and I was done with everybody at my freshman year. But my sophomore year, I didn't hate everybody quite as much. But then my sophomore year, I went up to him and I said, "Sir," and he says, "Yes, yes, Jason. What would you like?" I said, I noticed that I got a 97% on my exam, and my grade didn't go up any. And he basically turned to me and said, "Jason, if you're smart enough to get a 97% on your exam, then you're smart enough to figure out why your grade didn't go up. Now, get out of my face and go sit down." So that was the first time that I kind of pissed him off. And then the second time I pissed him off was I was sick. Oh, there's always one, and that was me. Yeah, exactly. I was the one, exactly. So I was that student, right? There's always that student that you're like, oh, this is we call them extra grace required students. Okay, they just need the extra grace, the extra patience, right? And that was me. That was me. So it's kind of, you know, again, it's whatever you want to call it, karma, or you know, what goes around comes around. You know, what what you sow you reap, right? So yeah, so I get to teach those people now that were me. It's kind of like that parent's curse, right? You get the parent's curse, where it's like what you did to your parents, your children are going to do to you. So yeah, and when you're a grandparent, you just sit back and laugh at them. You're like, yeah, you get to deal with teenagers too, right? So anyway, so the second time I pissed him off was I was out sick for a week, and after the week I turned in the homework, and I said, here's the homework from being out, and then he says, well, we have a test today. Do you want to study for the test? He's like, I said, no, I'll take the test today. He's like, you're gonna come and take the test after being out sick for a week? I said, yeah, I'll take the test. And he's like, okay. He's like, well, why do you think you can take the test? I said, because I did all the work. He's like, well, how did you know how to do all the work? I said, I read the book. And then I turned to him and I said, you know what? I don't even know why I even need you. And then he turned to me and he said, Jason, he said, you do realize one thing, right? And I said, what? He says, you're not normal. and that was kind of like an interesting, you know, he's like, that's not typical. And I was like, oh, you know what? You're probably right. I was like, you're probably right. Well, he got me back a little bit later on in the year as well. He was a very smart man, very wise man. Okay, that's why I went back to student teach from him when I was 23. So he later on in that year, I went up to the pencil sharpener. We had pencil sharpeners back then in the rooms. This was in the early 90s. And we had pencil sharpeners in the room. I went up to the pencil sharpener. I could not get my pencil in the sharpener. The pencil. I just kept trying. I just kept putting it in it. He turned at me and he looked at me. He walked over to the pencil sharpener and he turned this little dial on it. And then he stuck my pencil in and he turned to me and he said, Jason, stick with the math. I said, okay, probably a good idea. So, and that's what I did. I stuck with the math because obviously at that point I knew common sense was not my strong suit and I had to go with my strengths. So anyway, I digress. I always digress, but you know, I think these are important things to share. Okay, so we all have our strengths and we all have our weaknesses. Okay, so the doubling time for this thing is t equals natural log of 2 over r. Okay, let's talk about the population growth. If p equals p naught e to the negative rt, then the population, okay, is dying. Okay, the population is decaying. Okay, the population follows an exponential decay. Whoops, forgot my A. Decay model. Okay, it follows an exponential decay model. Okay, so we have dp dt in this case. Okay, dp dt is equal to negative rp. Okay, dp dt is negative rp, where r is the exponential decay rate. It's the exponential decay. Now notice the only difference between this equation and the other one is the negative sign. Okay, it's now a negative rate or a rate of decay. And so because we have that negative sign, what happens to our range, okay, our values is they get mirrored. It's a mirror image. It's symmetry across, they get rotated across the y-axis and it now gets exponential decay. Okay, it goes down exponentially instead of up. And I gotta get better at writing these things here. And where is this point? Where is this initial value that we start with? That's P naught. Okay, P naught. Okay. Not to be confused with peanut, which makes a very delicious butter. Okay, but it's P naught. Okay. Okay, so that's our initial amount, right? That's our initial amount. Okay, it's our initial amount. Okay, let's do one from, I don't know if this is biology or chemistry. Well, I'm just going to go with chemistry at this point. Okay, so chemistry people don't get a lot of you know, props, and I believe that we do have one chemist in here. So well, I'm just going to go with chemistry on this one. Okay, so strontium, okay, 90. Okay, there you go. Beta decay. Okay, strontium 90 has a decay rate decay rate of 2.8% per year. Okay, 2.8% per year. The ratio of change, in the amount N of this radioactive isotope, is given by, okay, dN dt is equal to 0.028 N. Okay, write my N better. Okay, so that's the differential equation that we're going to be working with here. Okay, if this is the differential equation, we're going to eventually need to translate that into a if there's a negative here, sorry, there's a negative. Otherwise, it'd be exponential growth. It's exponential decay. Okay, so there's a negative. It's negative 0.028. Okay, how much? Let's answer this question. How much? Did I mess up again? Did I chat? Oh, what did it say after strontium? 90. Just strontium 90. It's just dash 90. 90. Okay. Strontium 90. I don't know. It really doesn't matter for the problem. We could care less. I just want to focus on the math. Okay. It could be carbon 90, however you want to do it. Okay. What it is doesn't really matter as much as how it behaves. We want to know, how does this thing behave? Okay. How much of 1,000 grams of strontium, okay, okay, is left over, okay, after 70 years? Okay, how much of this is left over after 70 years? Well, we need to know what's the original growth model on this thing, right? So we have dN, get rid of this thing. Okay, we have dN dt is equal to negative 0.028 N. How much of 1,000 grams of strontium is left over after 70 years? So what would be the exponential decay model here would be N is equal to, okay, we'll go N naught, okay, N naught for our population growth, N naught E to the RT, right, RT, okay, and it's negative this time because it's decay. Okay, so what goes in for N naught? Well, that's 1,000. What's our decay rate? Well, that's 0.028, and then what's our time? Our time is 70 years, right? So if we plug all of this, this is equals. If we plug all of this into a calculator, we would come out with 140.9 grams about. Okay, so after 70 years, about almost 9/10 of this thing is gone. Okay. Oh, did I mess up? Oh yeah, negative. Thank you. Yes. Okay. Okay. So what about B here? Let's do question B. B says, how long, okay, will it take, okay, how long will it take to have half, okay, have half as much strontium? 90. Okay, how long until it has half as much? Well, let's go back to our formula here. N, whoops, not N naught, N. N is equal to N naught e to the negative RT, right? Okay, so what do we want? We want half as much, right? We want half as much. So if I start with 1,000 grams, how much is half of that? Well, it's 500, right? So that's 1,000 e to the negative 0.028 t. Okay, so what we want to do is, again, we want to solve for t. Okay, okay. So divide by 1,000. We're going to get 1/2 is equal to e to the negative 0.028 t. Take the natural log of both sides, ln, that cancels. I get the natural log of 0.5 is equal to negative 0.028 t. So now I'm just going to divide by my rate, negative 0.028, negative 0.028, and I get t equaling natural log of 0.5 over negative 0.028, right? Okay, and this should give me my time to cut this thing in half. Anybody know what that's called? To cut something in half? Half-life, exactly. Very good. Thank you. Okay, yes, this is the half-life. Okay, and I did not know this until I married a nurse, that in medicine, the most, when the medicine is working the best in your body is right at the halfway mark. I didn't realize that. That's why they count half-lives in medicine. I did not know that until I married a nurse. She says, oh, by the way, yeah, the half-life of this medicine is this. And I'm like, well, why do you, because I asked her, I'm like, well, that's not when all of the medicine is out of your body. And she's like, no, that's when there's that's when it's the most active. I'm like, oh, interesting. Okay. Well, they would give you the half-life, Sierra. They would say, you know, does that make sense? They'd say, oh, the half-life is 70 years, right? In which case it would be basically part A. That's a much easier, if they give you the time, the half-life, okay, it's a much easier question. Sometimes you might need to solve for the rate. So that is a good question. So sometimes you might need to solve for the rate. Now, would I give you that on an exam? I don't know. I don't think so. But because I'm more interested in the calculus at this point than whether or not you know how to do the algebra. Okay, if I'm testing you on algebra, that's a complete waste of time for you to be in this class. I want to make sure you know how to do the calculus. Okay, does that make sense? Okay, but yeah, so it depends on what you're solving for. Are you given, you know, a certain amount, blah blah. But that's more for a pre-calc class where you have time to. We don't have time in this class, honestly, to go through all the ins and outs of here's that's why it's here's an example, here's how to do it. Just do it. But in the homework, they may ask you that. So yes, be prepared that they may ask you what's the decay rate of a certain half-life. Okay, but again, you would just take the natural log of both sides and solve. Same deal here. Okay, so t. Okay, t is equal to ln 0.5 over negative 0.028. Okay, and so the time here is approximately, if I did this correctly, it's 24.76 years. Okay, for this thing to decay half as much. Okay, so that's the time that it takes to get half as much. Okay, and again, going back to Sierra's question, okay, if they gave me half-life and they wanted me to solve for the rate, I could do that, right? Because if they gave me the half-life and I want to solve for the rate of decay, well, wouldn't that just be, we'd end up with 1/2 on one side, right? And then we do e to the r, negative r, and then 25. I'll just round it to 25, right? So isn't this basically the same? It's basically the same problem. Okay, they have an inverse relationship to each other, half-life and decay rate. And it's a linear relationship. Okay? I mean, heck, you could even look at it like this, that the decay rate times the half-life is always going to be equal to ln 0.5. Okay? So that's another easy way to figure that out. Okay? Always good questions. Okay. Okay. So let's make it even more simpler. Let's make it even more simpler. Let's simplify the decay rate, and let's think about it this way, right? So if the decay rate is always t equals the natural log of 0.5 over r, right? Was it r or negative r? Oh, it was negative r. I'm sorry. This should be negative r. Okay, because r is the decay rate, but there's a negative there. Okay, so over negative r. Well, is there a different way that I could write natural log of 0.5? Well, yeah, absolutely there is. Let's do natural log of 1/2 over negative r. Well, I can rewrite this 1/2 as natural log of 2 to the negative first power over negative r, but using the property of logs, can't I just bring that negative 1 in front? And wouldn't that just be negative natural log 2 over negative r? And the negatives cancel out, which gives me natural log 2 over r. Well, that's great. This is your half-life formula. That formula is very similar to another formula that I just had. What was the formula that I just had? It's the same darn formula. Oh my gosh, look at that. Let me scroll back. It's the exact same formula for doubling time. Oh, look at that. That is some cool stuff. Half-life and doubling time use the same formula. Huh. That is some beautiful math there. That just makes me excited to be alive today. Okay, that is the universe is singing today in this class because it's so beautiful. It's so amazing. Okay, half-life formula, doubling formula, sweet. Okay, so the present value, going back to finance. Okay, the present value. Okay, of an amount f, okay, due t years later, okay, at interest rate r, compounded continually. Okay, the present value of an amount f due t years, okay, of an amount f, okay, due t years later at interest rate r, compounded continually, comma, is given by p equals f e to the negative rt. Okay, that's the present value formula. It's exponential decay model. Okay, now how did we get this formula? Well, it was actually very simple. Okay, it was very simple. Remember this formula? P e to the rt. Isn't that my exponential growth in my PERT account? Right? What would F stand for? F would stand for future value. Future value. Ooh, future. Into the future. Okay, future value. What would P stand for? P stands for my present value, or my principal amount, or the initial amount. Right? So present value. And how could I solve for P? What would I do to solve for P in this equation? Okay, all you math geniuses know exactly what to do. P is equal to F over E to the RT, right? But now we have the exponential in the denominator, right? Which is the same as a negative exponent. So isn't this going to be equal to F E to the negative RT, which is an exponential decay model? Just say yes. Just humor me. Okay. You're like, yes, of course it is. Professor Holtman, I knew that from the beginning. Okay. I don't even need you. Okay. Okay. So let's do one final question. Let's do one final question here. I'm not going to cover Newton's rate of cooling. You can read about that in the book if you want, or it's just plug and play basically. You know, I want to focus on the calculus. That doesn't really have any calculus in it. And so I really want to focus on the calculus. You will not have a Newton's rate of cooling problem on the exam. It will not be there. Why? Because it's not calculus based. Does that make sense? Okay, this is a calculus class. I want to test you on the calculus. Okay, but Newton's rate of cooling is a part of, okay. The exam questions from WebAssign? Yes, but I pick the questions. I hand select the ripest questions from the tree of knowledge for you guys so that I can deliver them in a palatable form through WebAssign. It's good stuff. Okay. Okay. So number 4, new grandparents. I also don't reuse questions. So all the questions on the exam are going to be what do you call it? There's no repeats. They're all unique. Okay, they're all unique questions. Okay, new grandparents want to invest, okay, an initial amount of money at 4% interest. Okay, so that what? So that their grandchild, okay, has $10,000 on their 20th birthday. $10,000, okay, on their 20th birthday. How much should be invested today? Okay, we're going to assume that the baby was just born. Okay, how much should be invested today? Okay, do the problem, put your answer in the chat box. Okay, try not to steal people's answers. Okay, given everything that we've gone over today, you should be able to handle this. Okay, let me know if you get stuck, honestly. Okay, you don't have a calculator on me right now? Okay. Okay, do you have internet access, don't you? Okay. Sierra, why are you so scared about the exams? Is there like, do they just like beat that into you at Berkeley? That like it's
Kind of, yeah. The exams at Berkeley are like a different breed. So,
okay,
but also I just like being prepared. It like helps my own like test anxiety.
right? Okay, that makes sense. Yeah. Okay. I mean, it is high stakes. I get it. I get it. But I mean, you're already there, so I mean, you plan on going to grad school?
I'm not sure for econ, but maybe
Maybe.
like
Yeah. Okay.
yeah.
Okay.
Econ in grad school uses a lot of calculus. I know.
Yeah. Yeah.
I'm not
Absolutely.
sure I'm ready for that.
Yeah. Separates kind of the people who just want to do business from the people who want to really get into economics, macro, micro theory, basically, right? Okay. So a lot of people are stealing my answer here. Okay. Of 44,093.29. That is my answer. Okay. Is anybody confused how I got that answer? Yes. Okay. So Frederick says yes, he is confused how I got that answer. Okay. So let me go in and let me unconfuse you. Okay, real quick. Okay. So what's the formula? Formula for present value, or sorry, for yeah, for present value, right? So present value is equal to, okay, F e to the negative RT, right? Okay. So what does F stand for? F stands for my future value or my final value. P is my present value. That's how much I need to invest in today. Okay, present value. Okay, so what I'm looking for is the present value. That's the value, that's the amount that these people need to invest for their grandchildren, their grandchild today. But what do I want the final value to accumulate to? Well, I want the final value to accumulate to $10,000. So that's going to be E to the negative, what's the rate? Negative 0.04 times 20. Okay, and then if I just plug that into a calculator, that becomes $4,493.29, which is roughly, I would just say, hey, you know what, invest $4,500 and you're going to be safe. Okay, so invest $4,500 today and that'll pay for half a year of college. There you go. Okay. No, that's fine. That's fine. Absolutely. All you had to have done was divide. Okay. You can use either formula. Okay. I'll stick around to field any other questions that you have at this point in time. Otherwise, you are free to go. Okay, that is the end of the notes for today.
Do you still have office hours as usual next Tuesday before the
Yes,
exam?
yes.
Okay.
This is Sierra.
Okay, thank you.
Oh,
Yeah.
oh, yeah, of course it was. Okay, sorry. Just kidding. Okay, yes, I will have office hours an hour before the exam to keep you guys from freaking out. Okay, I am a fair grader, so just letting you know. Okay.
Thanks, Professor. I've gone.
Oh, thank you. Thank you very much.
Excuse me,
Yes?
Professor.
Yes.
So the exam's gonna be in the beginning of class on Tuesday?
Yes. It will be during class on Tuesday.
Okay.
So if you
Thank you,
look at the syllabus, there is a schedule on the
Yeah.
syllabus for the exams. And you
Okay.
need to make sure that you've signed up for WebAssign. So read through the syllabus because all the homework, Isabel, is in WebAssign.
Okay.
Okay?
Thank you, Professor.
Sure.
Bye, Professor.
Bye.
Excuse me, Professor.
Yeah, sure.
Is there going to be any supplementary material for the exam, or should we be good just going over the homework?
No, I'm actually going to, thank you for reminding me, I'm going to post an exam review right now.
Okay, thank you.
Okay. Try to get
Yeah.
that out a week early, but during summer school, it's like a week early is like worth 4 weeks, a month early. So
Yeah.
it's tough. It's tough.
I understand.
So, but yeah, I'm going to put that out to right now as we get off.
Got
Okay.
it, thank you.
Okay.
Professor, could I ask you about the homework section 6.3, question number 9?
Yeah. One second. Let me stop the recording for right now, and then let me stop my share, and I'm going to stop the recording.